If you're one of the spotlight speakers, can you come sit in the front? There's a special seat for you.
Welcome to the Machine Learning for Computer Vision session. I'm Philip, and
I'm Olga. Philip is from UT Austin. I'm from Princeton. So this will be, we'll have 3 talks, 12 minutes each, with some time for some questions afterwards. So please think of questions, and also please line up by the mics on either side. After that, we'll have 13 quick spotlights. There will be no questions for the spotlights. If you're one of the spotlight presenters, please come sit in the front. There's a special chair for you. Yeah, you'll just line up once the oral sessions are complete. All right. With that, it's my pleasure to introduce the first talk by Henriques and Andrea Vedaldi, talking about allocentric spatial memory for mapping environments.
Thanks. Hi everyone. I'm João. I'm here to present some joint work with Andrea Vedaldi at the VGG in Oxford. Okay, so I'll start with the motivation for our work. In computer vision, very often we consider tasks that are actually defined in image space. So for example, detecting objects and segmenting them and extracting 3D information such as depth maps and things like that. So these can be very useful, as you know, but they're all image-centric tasks. Now, ideally, we would like to go further than this, because if you want to have autonomous agents in the world and acting in it, you want them to reason beyond the image and into the world to enable things such as long-term planning. So, for example, if an object enters the camera view and then exits it, you want the agent to retain the notion that the object exists, which is commonly referred to as object permanence. Okay, so one step towards this world-centric understanding is to just create a map of the environment and place the agent within it. A problem that's referred to as simultaneous localization and mapping, or SLAM for short. Typically, the agent observes one frame at a time and incrementally creates a map and localizes itself with respect to it. Now, of course, people have considered this problem before, and there's a very long tradition of doing this using classic algorithms from geometry and computer vision. While these approaches can work very well, they also have drawbacks. For example, adapting to new scenarios and environments might require extensive hand tuning, and another issue is that there's no semantic information really, and there's no prior information that can be leveraged to compensate for missing data, which happens very often due to the limited viewpoint. So the question in everyone's minds is, how can we solve this with deep learning? And this in theory could address all of the previous points. One approach is to just train a deep network to estimate the ego motion from which a position can be recovered. But this has the issue that it lacks the mapping component and thus does not really build a word representation that can be useful later. Another direction has been to train a network to regress the camera position from images for a particular environment. In this case, the mapping actually occurs offline, and the map is embedded implicitly in the network parameters. So unfortunately, deploying this kind of system on a new environment always requires retraining. Recognizing this problem, some people recently have considered building the map online to be able to quickly generalize to new environments. In this case, the map is part of the network's activations, which is ideal. However, because this brings additional complexity, they usually assume that perfect ego motion is given as input, so they're not really solving the localization part of the full SLAM problem. So in this work, we perform both mapping and localization with a deep network, where the map is incrementally built online. This means that we're performing localization based on the actual map that's currently being estimated, and for this reason, we do not assume any given ego motion or position information. The key ingredient of our method is a new dynamic memory that can be used by a neural network to store and incrementally update information about the environment. Now, crucially, this information is allocentric rather than egocentric, in the sense that the map coordinate system is relative to the world rather than the agent. The map is simply a 2D grid of cells, and each one stores one vector embedding. This allows associating both geometric and semantic information with each discretized location in the world. A nice property of our model is that we can perform localization and mapping as a dual pair of efficient operators. First, we show that we can reduce localization to the convolution of an image embedding with the map memory. And second, we show that the mapping operation mostly consists of a single deconvolution, which is the dual operation to the convolution we use for localization. So in essence, mapping is the dual of localization, and they are implemented as convolution and deconvolution, which I think has a very satisfying symmetry to it. So in order to dive into the details, I'll explain first the image embedding component. The goal of this component is to project the image-based embedding computed by a CNN into the ground plane in a way which is compatible with the 2D map coordinate system. Now, this is a simple geometric projection, and it can be done in closed form, given a depth estimate and the camera intrinsic parameters. So in our case, we assume that a calibrated RGBD camera is available. Now that you've brought the pixels to the ground plane, the next step is localization. And this step takes this embedding and compares it to the current map memory. This can be done simply by an exhaustive search over all possible positions in the map. Now, this may sound very expensive, but in practice, it just amounts to a simple cross-correlation operation, which is implemented as a standard convolution. After that, we convert it to a normalized probability map of the agent's location using softmax. Note that in this way of working, matching is done globally against the full map at every step. This is important because it allows the model to represent ambiguous beliefs about its position, as we'll show in the experiments. Of course, if we do dense matching by convolution, we're only considering translation of the camera. So to be useful for mobile robotics applications, we need to also consider rotations of the camera, at least in the ground plane. And it turns out that this can be implemented simply by rotating the local view the local views embedding in the ground plane several times, and using these rotated views as a filter bank for the convolution. The result of this operation is a joint probability map of positions and orientations, with the orientations just stacked along the third dimension. So just to take a step back and see what this all represents, with these simple operations, we're transitioning from the camera reference frame, coming from the input image on the left, to a world reference frame in the map and location estimates. The final operation is to incrementally take information from the local view and integrate it in the map. In order to make this easy, we need to register the local view with respect to the world space coordinates. And if we do this, it's easy then to integrate it by just linear interpolation or another update mechanism. So in this paper, we show that deconvolving the position and orientation heat map with the same filter bank of local views achieves exactly this. Intuitively, if there's a single peak at a particular position and orientation, as shown on the left, the convolution takes the corresponding rotated local view and places it into that exact position, so achieving registration. In the end, we just integrate this new information with the previous map with an off-the-shelf convolutional LSTM. So here's the full pipeline with all the things I described. We essentially ground project the CNN features, create a rotation filter bank, and then apply the convolution and deconvolution pair to both localize the camera and register the local view, which gets integrated into the map memory. As I mentioned at the start, the main two components are the convolution and deconvolution in map space, which efficiently implements localization and mapping. Okay, so now we can move on to the experiments. As a first investigation into this approach, we consider a toy problem of localization and mapping in small 2D mazes. In this case, there's an agent moving randomly with limited visibility, and this agent cannot see through walls since its observations are local. So even as the view rotates, the observations are always right aligned, which you can see in the image on the right. We trained our MapNet model with the input sequences of 5 frames and just trained it in a supervised manner to minimize the error of the position and orientation prediction. Now I'm going to show an example sequence from this task. You can see the agent as a red dot on the left. And in the first frame, its local view looks like what's shown at the top. The position heat map is shown below, ignoring orientations just to make it easier to visualize. In this heat map, brighter cells denote higher confidence in the position, and the ground truth is shown in blue. As the sequence progresses, you can see the network predicting correctly the current position, even though it's given only a very incomplete local view with unknown orientation. I think this is quite a non-trivial behavior because the SLAM task essentially amounts to stitching the local views together like puzzle pieces based on their overlap to create a larger map. Another interesting example is when there is ambiguity in the data. In this case, the corridor in the first frame looks exactly the same on both ends. So the second frame's local view can fit either end of the corridor. Interestingly, the MapNet models this ambiguity as a multimodal heat map with 2 competing hypotheses, one above and another below. But as more frames are observed and evidence is gathered, eventually one of the hypotheses dies out because it just doesn't fit the data that well. So you may wonder what the maps look like, and the fact is that they're actually not always that interpretable. Here I'm showing one channel of the map in each column with brighter cells denoting higher values of the map embedding. You can identify some features such as free space or walls, but the important point is that we can observe that the map's extent is larger than any individual view, which is what we actually want to achieve when mapping. And because these embeddings are not very interpretable, we try to see if they hold any semantic meaning. And to test this, we trained classifiers based on these embeddings, just to discriminate between known features of the mazes, such as corridors or turns or dead ends or forks. And the gist of these experiments is just that the embeddings correlate highly with semantic features, since the prediction accuracy based on these features is well above chance level. Now, obviously, we didn't want to just limit ourselves to toy data, so we scaled up by trying the same system on 3D data from the game Doom. In this case, we took several hours of recorded speedruns by experienced players, removed the monsters and sprites, and asked the network to perform SLAM from these images. This represents a very large scale and visually diverse dataset. In this video, you can see some qualitative results with the estimated position heat map and trajectory shown below, and the orientation heat map shown on the right. So the great thing about an end-to-end learnable system is that it's easy to just get new data and train it, even if the characteristics of the data set are very different. And as a demonstration, we took the same system and applied it to a real-world robotics data set, the active vision data set. So we did some quantitative comparisons, focusing on localization accuracy, and the takeaway is just that while visual odometry has good performance for short sequences, it will eventually suffer from drift, while our model actually matches a map and fares better in the long term. And classical systems such as OrbSLAM don't really do that well because active vision dataset, it has a very low frame rate video. So in conclusion, we performed SLAM entirely online using an end-to-end learned architecture. We found that localization and mapping can be expressed as a dual pair of convolution and deconvolution, and semantic embeddings of the world arise naturally from the self-localization objective. So that's all, and thank you.
If you have any questions, please line up. Yeah.
Hi, I have a question. So typically in mapping, you do not know the size of the map ahead of time. So how do you determine the size of your memory and the resolution?
In this case, we sort of just guessed and just made sure it was big enough. So when training, because we're only training with 5 frames at a time, we can get away with a very small map. And then during online operation, we just consider a much larger map to make sure that the camera doesn't go outside of the boundaries. But if you really wanted to make something more robust over long time frames, you could do something like a rolling buffer and that kind of thing.
And the size of the grid or the resolution, does it matter or no?
Here, we just had the 30 by 30 map. And the view usually goes up to like 15 cells or something like that, and they correspond to around 30 centimeters in real world. So it's quite a few meters.
So it's already kind of determined your little bit of prior knowledge of what kind of data you will be.
Yeah, it depends on the relative speed of the agent and things like that. So you have to initialize the tensor with some size. We just took one. We found was good. Yeah.
Okay, so you compared with a data set where OrbSLAM didn't do well, but it's well known to work in many different data sets, environments. So did you compare your system in environments where OrbSLAM does really well?
So I didn't, because this really doesn't, this does not deal with free-form rotations or translation, and also because we have a very coarse discretization grid. As I mentioned, it's about 30 centimeters in the real world, so it's not really the point. So we wanted to focus on something that looks like mobile robotics applications, and that's why we went with the active vision dataset, where you have this sort of situation.
We'll take one more question.
Hi, so great talk. So I was wondering how you handle the cases of multiple floors and how you resolve the ambiguities between floors.
We didn't, but I think I would say it would be pretty easy to just have the tensor have multiple levels and localize in Z. I mean, obviously, you can't just have arbitrary, if you have arbitrary voxels, then it's going to slow down a lot. But for a few levels, I think it should be fine.
Okay, thanks.
Yeah. All right, let's thank the speaker again. All right, next up, we'll have Apratim, and he's going to talk about accurate and diverse sampling of sequences based on best of many sampling objective.
Hi. We are from the MPI in Saarbrücken, and today we shall talk about sequence prediction. What do we mean by sequence prediction? That means we aim to predict future C sequences given the initial observed C sequence. For example, consider this from the Stanford drone dataset, where the initial pedestrian trajectory is shown in white. Our task here would be to predict the future location of the pedestrian. Recently, these sort of works have gained prominence. For example, in many diverse areas, ranging from autonomous driving to robotics, because many important tasks can be cast into the sequence prediction framework. For example, works in the area of pedestrian prediction, video frame prediction, among many others. If we analyze these works in detail, we see that conditional variational autoencoder-based approaches achieve state-of-the-art results in these tasks. So let us go back to our motivating example and see what a conditional variational autoencoder would do for our pedestrian trajectory prediction problem. On the right, we can see the sample futures from a conditional variational autoencoder. However, this leaves much to be desired, mainly because the few futures look almost uniform, and they do not correspond to the modes of the true underlying data distribution. Therefore, in this work, our key contribution is to develop a new training objective. And we shall show that our objective leads to better results compared to the standard conditional variational autoencoder. For example, let us go back to our motivating example. These are some futures that are sampled by our best of many sample-based objective. These are predictions, and as you can see, compared to the conditional variational autoencoder, ours are more diverse and the modes are more prominent, and yeah, it captures the underlying data distribution much better. This motivating example highlights the key challenges that we face in sequence prediction, namely uncertainty and multimodality. In the rest of the talk, we shall discuss how exactly we address these key challenges. Okay, similar to conditional variational autoencoders, we base ourselves on conditional generative model. This is a conditional generative model, which is shown here on the right. In the following, we shall discuss how can we sample from such a conditional generative model, and more importantly, we shall discuss how we can train such a model, and in particular, we shall discuss our best of many sample objective and this is the standard conditional variational autoencoder based objective. So conditional generative models are powerful tools to learn complex conditional distributions. For example, here, given the initial observed trajectory x, we can, a conditional generative model can be used to learn the conditional distribution that is p of y given x. And from this, we can generate our future trajectories as samples. The crucial component here is the latent variable z. This is what really enables us to sample diverse and multimodal futures. Next, we come back to sampling in detail. So how do you actually sample from this? The crucial component, again, is to sample the latent variable z's first. Given these latent variables, we can now proceed to sampling from our future trajectory distribution, like as shown here. Okay, now we come back to the more important aspect of training. So how do you do this? So always, if you train a model in machine learning, we have to always estimate the loss. That is given a training example, we need to estimate the likelihood assigned to this training example by our model. How do you do this? A naive approach would be to do MC sampling of the latent variable. However, this may be suboptimal, as we might completely fail to explain the training example, because in normal scenarios, we are constrained to use only a few samples during training. Consider this, for example, on the left, our model at training using MC sampling would completely fail to go to the correct mode. This leads to high variance updates, which is bad for training. Therefore, the standard approach in literature is to use a proposal distribution, that is to use importance sampling during training. Okay, so that means now we proceed to actually sample from the proposal distribution, which we jointly learn during training. And then we shall be able to generate samples that explain the training example at hand during training. This leads us directly to the standard conditional variational autoencoder objective shown at the bottom. The main problem that we identified here is that the likelihood of all the generated trajectories is averaged. This puts a strong constraint on the proposal distribution, and therefore we are forced to trade off between a good estimate of the data log likelihood and the divergence between the true and the proposal latent variable distributions. This is really bad because during evaluation, we do not have access to this proposal distribution, and a large divergence between these two distributions during training and test time would lead to bad performance. Therefore, we aim to mitigate this problem with our best of many sample objective. How do you do this? We keep you using the standard importance sampling trick. However, our objective is different. Instead of taking the average likelihood of all the generated samples, we instead take the likelihood of the best sample. Okay, why we do this? The full derivation of this is in the main paper. Please refer to this. However, we shall not go into these details. We shall motivate this more intuitively in the following. Okay, so as the model needs to produce at least one good sample, this encourages the model to make more diverse predictions. And because of this, it loosens the constraints on the proposal distribution and allows it to more closely match the true latent variable distribution. So therefore, our pipelines during training and test time are more aligned, and hopefully during evaluation or when we use it in the real world, we shall hopefully get better results. Actually, we show that we get this in the following. Okay, so as data sets, we consider 3 data sets. First 2 are trajectory or sequence trajectory prediction data sets. The last one is a video prediction data set. So we can do any sort of sequences, videos, and anything that we want. But okay, in this talk, we shall only focus on the first 2. What is the first one? The first one is the MNIST, is extracted from the MNIST data set. This actually corresponds to the actual handwriting strokes that are existent in the MNIST data set. The second one is the Stanford drone, which consists of pedestrians captured on board a drone. Yeah, so for our model architecture, because our main objective is to compare the objectives, we keep our model architecture simple, but corresponding to what is present in the literature. It's a simple RNN encoder decoder type architecture, which has, again, an RNN recognition network, which is used to train the proposal distribution during training, which is not available during test time. And of course, by varying the Z, we can sample the different Ys or Y hat as samples. And as main metric, we consider the conditional log likelihood, which measures the match between the predicted and true distributions. Okay, MNIST handwriting strokes gives us a good starting point to look at the diversity of our predictions. For example, consider the initial observed trajectory in white, and these are the predictions by our model. Okay, this doesn't make too much sense right now, so what we can do now is we can cluster our predictions, and we can see these are the main dominant clusters, and which correspond to well-known digits like 0, 3, 2, etc. etc. So we see that our best of many sample objective leads to diverse predictions, which are multimodal. Okay, we can analyze this quantitatively. Using the conditional log likelihood metric, we see that we get better match to the underlying data distribution compared to using the standard conditional variation autoencoder. And and we can also analyze the accuracy of our model. For example, consider these initial observation. This is the actual ground truth in blue. And these are the best predictions, or at mean top 10% of predictions by conditional variation autoencoder. And these are the corresponding predictions by mean top 10% predictions by a best of many sample-based model. And we see that they correspond closer to the ground truth, which shows that our model is more accurate. Moving on to a more real-world data set, we have the Stanford drone. And again, we see more accurate predictions. For example, given this initial observation, these are the future ground truths. These are the corresponding best mean top 10% of variation autoencoders examples, and these are the top 10% of our predictions, which correspond closer to the ground truth. We, again, compare to the state of the art. We beat the state of the art in this data set, both on the conditional log likelihood and this is the mean top 10% Euclidean distance at test time. So our best of many sample objective leads to better fit to the data distribution and makes more accurate predictions. Coming to the end, to the conclusion, we have proposed a new optimization scheme for sequence prediction. We have observed that compared to the conditional variation autoencoder objective, we obtain more diverse predictions and more accurate predictions, and we obtain state-of-the-art results on 3 data sets. Results on video prediction can be found at our poster, which is C3, and please come by to ask any questions that you may have. Thank you.
Please line up for questions.
Hi, thank you for the good talk. Before I ask my question, I have to apologize. There's always a grumpy questioner that comes your way.
Okay.
I apologize. That's me today. I think you're missing connections to an entire line of work.
Okay.
And the grumpy part is that it's coming, some of it, from me.
Okay.
This best of many objective has a name. It's actually called multiple choice learning. There was a paper back in NIPS 2012 where you write down max over the of multiple predictors that you train over the loss function. There's actually a follow-up line of work from Drew Bagnall's students, Debadeepta Day, for robotic applications, which actually shows that some of this has connections to submodular maximization. I encourage you to look into that line of work. It's actually a really interesting sort of connections to submodularity. So in addition to just being grumpy, I guess I will ask a genuine question. Have you thought about connections to submodularity in that sense, and how you might measure improvements for the diversity and the coverage terms?
So, okay, so first, to coming back to the first point, we have seen the paper on multiple choice learning, and we have seen other papers that do best of best of many. But please know that we are dealing with conditional generative models, and this is the first work that does this. We claim this very clearly. We do not ever claim that it's the first idea. There are multiple papers with similar idea, but we show that even for conditional generative model, such a objective makes sense. So please, if there are any missing citations, we shall update that again. Please come with any questions.
And I'm happy to connect offline on that.
Yes, of course.
Thank you.
Yeah.
Time for maybe one more question. All right, let's thank the speaker again. While the next speaker sets up, if you're giving a spotlight, we're still missing quite a few spotlight speakers. If you're one of the spotlight speakers, please come sit in the front in the assigned seats so we know that you're here. All right, so next up we have Xavier Puig, who's presenting work with his co-authors, Kevin Rama, Marko, Boben, Jiaman Li, Tingwu, Wang, Sanja, Fidler, and Antonio Torralba on simulating household activities.
Thank you, Ola. So, hello everyone. My name is Xavier Puig, and I'm going to present our work on VirtualHome, simulating household activities via programs. This is joint work with Kevin Rama, Marko, Boben, Jiaman Li, Tingwu, Wang, Sanja, Fidler, and Antonio Torralba. Imagine this woman has just got a robot to help her with tasks at home. For example, make a margarita. This robot could be pre-programmed to know how to do the drink, knowing all the steps that are required to do so. But this woman and her dog's expectations are high. So now the robot needs to adapt and learn how to perform many things it was not programmed to do. So how could it do so? Well, if we humans had to learn a new task that we didn't know how to do, we'd probably go to the internet and search for information about it. For instance, if we wanted to know how to make a tea, we'll try to pull some instructions on how this is done and read through it to know how to make the tea. Now, for a robot to know how to do the task, these instructions need to be given in a language that it can understand. Notice that this description here is missing many steps that we consider common sense, but a robot needs to know in order to execute the activity. For example, for boiling water, it needs to know that it needs to grab a kettle, fill it with water, put it on the stove, and so on. Instead, we could give the robot a program containing all the steps that are required to do this activity, so that the robot could execute it and perform the task that it's asked to do. Now, these programs can be used to drive a robot to perform different tasks at home, but they are indeed more general, and they can also be used to drive an agent inside a virtual house. So by creating an environment where these programs can be executed, we can simulate complex tasks before performing them in the real world. As our first step, we aim to collect a knowledge base of diverse activities. And remember that we aim to collect this aimed at robots, meaning that we want programs with all the instructions representing these activities. Of course, we want to scale this knowledge base beyond the programming-savvy grad student. So we aim to collect those tasks via crowdsourcing. And we do this in multiple steps. First, we ask people to name an activity they would typically do at home, and ask them to provide a description as if they had to teach another person to do it. On the late stage, we take this description and show it to a different worker so that they can provide a program containing all the steps so that a robot could execute it. Now, many people on Amazon don't know how to program, and this makes it a pretty challenging task. To do so, we take inspiration from Scratch, which is a programming tool designed at MIT to teach kids how to program. And the idea is that kids drag and drop blocks of instructions as if they were Lego pieces to build video games or videos. What we did was to design a programming language where each block would represent an atomic action that an agent could execute, and ask people to connect these blocks together to generate sequences of actions that could represent activities. Now, for example, for setting up a table, we'll be looking for a program like this, with all the sequences of instructions that are required. Grabbing a plate, putting it on the table, and doing it the same with a fork. It took some time and some training, but after a while, we actually managed to teach people on Amazon to program. And they actually came up with pretty complex programs. For example, for an activity such as Thanksgiving, they would give us long and complex programs depicting how to set up the table for the occasion or how to prepare the turkey. And we even got instructions on how to do research, with very detailed steps like open the Word, read from books, search on the internet. Now, the same activity can be done in multiple ways, and this is reflected in our knowledge base. These are 3 programs representing making coffee. Now, some people may like to make coffee with a coffee maker or with a kettle or with sugar and milk, and this is represented in our different programs. Altogether, our collected knowledge base contains 2,800 different programs corresponding to 600 activities. As I mentioned, each program is a sequence of steps that contain atomic actions and optionally an object that the agent interacts with. So altogether, we had 75 different actions and 300 different objects of interaction. And given these instructions, or these programs, we can compare them by comparing their instructions. And this allows us to measure similarities between the programs. So what this shows is for a subset of activities, their similarities according to how similar the programs are. So we now have our knowledge base of tasks, and our next step is to build a virtual environment where these tasks can be performed. Now, many simulators have been developed over the recent years, and most of which have been focusing on doing navigation or performing like small interactions in the home. We are rather interested in an environment where agents can perform small interactions that are compounded towards everyday tasks. With that in mind, we built VirtualHome using the environment, using Unity. VirtualHome contains 6 different apartments which are fully furnished so that agents can perform the activities. Their objects are made interactable and they're animated so that they change their state when agents act on them, making for real simulations. So we now have this environment when agents can play, and we need to be able to execute the actions in our programs. So given our 75 different actions, we took 17 of them and implemented them in the environment. For an action such as walking to the bathroom, we will take one of the apartments, check where the bathroom is, and use Unity's navigation package to drive the agent towards the environment. For other actions such as interacting, like here in grabbing glass, we would compute the agent's final position to the glass and perform inverse kinematics to realize a realistic animation. And we would do similarly with other actions such as opening, sitting, and so on, where we would also animate the objects to go for realistic animations. Notice that the same action can be done in multiple ways depending on the object you interact with, such as here switching on the TV or the lights. Of course, to create a realistic simulation, we also need to encode common sense in the environment. We need to feed the environment with information about what are the object's affordances or what are their physics. We don't want the agent to break the whole kitchen while creating a coffee. And this actually pinpoints why it's important to use simulators before doing things in the real world. Similarly, if the action involves watching TV, we want to make sure that the agent sits in a sofa before watching the TV. And we also need to make sure that the agent shoots for the mouth when drinking. Now, by performing optimization across the full program, our agent can now perform the full task. But perhaps even more than this. In the real world, we can instruct humans by telling them instructions of how to perform activities, such as my mother here in the left, or like watching TV and tweeting about this. We would like to be able to do the same with agents. We would like them to be able to show them a description of a task, or maybe a demonstration of this activity, and be able to perform the same actions that humans are doing. So we would like to take a description of a task, in general, and be able to generate the program that was creating it. Or similarly, we would like to take a demonstration of one activity, and again, generate the program that represents this activity. So let's first start on going from descriptions to actions. To do that, we will first take the description, encode each of the words using Word2Vec, and feed it into an LSTM encoder. And we will later use an LSTM decoder to generate our program, where we will predict an instruction at every time step by predicting its embedding. We will train the model using cross-entropy loss for every time step, and we will then fine-tune it using policy gradient, optimizing for 2 different rewards. First, we want our programs to be as similar as possible as the ground truth. And to do that, we measure the longest common subsequence between the predicted program and the ground truth and normalize it. The idea of this is that we don't want to penalize the model if it predicts an extra instruction, but the rest of the program is okay. Of course, we also want our programs to be executable in the environment. So to do that, we design a binary reward that tells whether our predicted program can be executed or not. Notice in this example that the program could not be executed because a Fritz cannot be opened when it's already open. So here's an example of the results of our model. Given this description, walk to the kitchen and put groceries in the fridge, we'll get this program where the model is incorrectly predicting one action at the beginning, which still makes sense with our description. And because of the way we measured our similarity measure, we would get a pretty good score. Now, sometimes our descriptions are not specific enough, and this leads to programs that, while may not correspond to the ground truth, they actually make sense, such as here for listening to music. We perform quantitative analysis by computing the desired metrics, similarity and executability. On the left, we show the result by randomly sampling a program, and in the middle, our model trained using cross-entropy loss. When we fine-tune with policy gradient, we can optimize both the similarity and executability. Now, for going to videos to programs, we first have to create a data set of videos representing these activities. To do that, we take our programs and simulate them in our environments by choosing a random apartment and a random agent, and adding multiple objects in the apartment, and then placing multiple cameras at different positions to generate diverse realistic videos of these activities. And because our data set is created using a game engine, we can obtain rich ground truth for our videos, including segmentation, optical flow, or timestamps of our atomic actions. To go from videos to programs, we use a similar architecture as before, but using an embedding for the video clips instead of the descriptions. To do so, we take our long video, split it into two overlapping clips, and for each clip, train a segmentation model using dilated net. We then feed this segmentation into a temporal reasoning network and predict an embedding representing the instruction of the action happening there, and use this as our embedding for every clip. So with this model, we can take one program of our activity, generate a video representing this activity, and then use the model to generate again one prediction that could be performed on a different environment. Notice on this example that the model is able to correctly pick switching on TV or sitting, but it's still missing the action watching TV. We somehow still need to add some common sense into the models. Now, in terms of quantitative results, our model outperforms the baselines in both metrics when using policy gradient. To summarize, we propose to represent complex activities as programs, and later designed a simulator where these programs can be executed to generate like these complex activities. We want to get diverse actions that are made at agents. So we crowdsource a data set of multiple activities with programs representing each of those activities. And using our simulator, we created videos that present these activities. Again, we want people without any programming experience to be able to drive these agents. So we designed models that can go from descriptions or video demonstrations back to these programs. This opens up exciting opportunities for the future, including modeling social activities, which actually appeared in our programs, or creating an RL platform to learn composite tasks given our programs. Now, like many of you, our robot is also eager to go watch the World Cup. So please join him on the poster C5 this afternoon. Thank you, everyone.
Any questions? All right, while we wait for the first question, I have one. So what happens if one of the commands fails in your programs? Like, let's say the fridge door falls down.
So this is something we solved afterwards in the environment, but what we have while it's running is a checker that checks whether at each time you can execute the environment. So if the agent goes and sits in a sofa that is not facing the TV and then has to watch the TV, the program will fail. And this is what serves as the binary reward to optimize our program generation.
You showed when you built the data set that for a specific task there would be multiple programs that would be compatible with that. In your last slide, function executability was part of the reward, but how, for example, making a coffee, in terms of reward, how do you which one is encouraged, for example, using sugar or not using sugar? How did you integrate that in training?
So at this moment, what we try to do is to predict the program that represents the video rather than the activity. So our similarity measure is what will be checking whether our predicted program is close to what the video is representing or not.
Okay, cool. Cheers.
All right, let's thank the speaker again. We'll now start our spotlight session. If you are a spotlight presenter and you're not sitting up front here, please come up front, otherwise we'll have to watch your presentation, awkward silence. All right, and the next spotlight presenter should always just line up here on the side, and I think that's all. We'll get started.
Hello everyone, I'm Yogesh Balaji. Today I'll be presenting our work, Generate to Adapt, Aligning Domains Using Generative Adversarial Networks. This is a joint work with my collaborators, Swami, Carlos, and Professor Chalapa at University of Maryland. Machine learning models are susceptible to domain shift. Models trained on one domain tend to perform poorly when tested on a different domain with varied domain statistics. Domain adaptation techniques make use of labeled source data and unlabeled target data to reduce this domain gap and train classifiers that perform well on both the domains. In this work, we propose a technique that performs domain adaptation using generative adversarial networks. Our pipeline consists of two parallel streams. The first one is a classification branch trained using supervised classification laws on the source data. The second branch is the generation branch that inverts the feature representations back into the image space. Both these models are trained jointly end-to-end. After the models are trained, we use only the F and C networks to make predictions at the test time. Next, let us look at how the networks are updated. First, let us focus on source domain data. In case of source data, the updates come from two branches. First, the F and C networks are updated using supervised cross-entropy laws. In the second branch, F, G, and D networks are updated so that the GAN model produces class-consistent images that look like source. For this, we use adversarial laws similar to the AC GAN framework. In case of target domain, we do not have target labels, so the classification branch cannot be updated. Our aim, however, is to make use of unlabeled target data to learn representations that are domain invariant. We do this by updating the feature network so that the target embedding produces source-like images when passed to the GAN model. It should be noted that only the feature network is updated in this step. This way of updating the feature network to produce cross-domain generations ensures that the source and the target embeddings are aligned. This is the core idea of our method. Next, let us look at the generated images. These are the results of the SVHN to MNIST experiment. And these are the results on the office dataset. We find that both source and the target data produce images that look like source. For the office dataset, however, we observe that the generated images are not realistic. Mode collapse occurs, resulting in reduced image quality. This is because the office dataset is a small-sized dataset with high variations, so training GANs are hard. However, even with such poor generations, our method was able to achieve good domain adaptation performance. This is because we do not use the GANs as a data augmentation method, but instead use it to train feature network to obtain domain invariant representations. Next, we plot the TSNE visualization of the feature embeddings. We observe that in case of source-only models, there is a clear separation between the source and the target embeddings. However, in our method, we observe that the source and the target embeddings are clustered together in a class-consistent manner. The following are the results we obtain. These are the results on digits dataset, the office dataset, and synthetic to real datasets. We observe that our method achieves good performance improvement compared to the baseline and other comparison methods on a range of benchmark domain adaptation datasets. We were also able to achieve good performance on the VISDA challenge. The code and the models are available online. Please visit our poster for more details and experiments. Thank you.
As you know, our paper is called MadGAN, and the video might go mad sometimes. It's not a bug, but a feature. I'm Arnab, and he's Vivek, and we are presenting our paper, Multi-Agent Diverse Generative Adversarial Networks, which we call as MadGAN. In this work, we focus on addressing the mode collapse problem in GANs. Before delving into the details of MadGAN, I'll begin with a few motivating results. We took a simple scenario of 1D mixture of Gaussians with overlapping modes. Given enough training data, ideally a GAN should be able to generate similar distribution as the training data. But as we know, and also evident from this 1D experiment, GANs suffer from mode collapse because the true equilibrium is hard to reach. However, as you can now see, our model MadGAN is able to capture almost all the modes. Briefly, our solution MadGAN mainly focuses on increasing the modeling capacity of GANs by increasing the number of generators. Here we show one real-world application on the image-to-image translation task, where conditional GANs are known to learn the delta distribution. Even on this challenging task, MadGAN is able to generate diverse and realistic images. Our main idea is built on the intuition that if a dataset has images of artworks by 3 different real artists and a single painter, as in the case of a vanilla GAN with a single generator, is given the task of painting all the different kinds, he would be overwhelmed and not be able to do any of the styles perfectly. To produce better results, we design a model with multiple generators, where the discriminator pushes each generator to master an individual style. We modify the objective function such that the discriminator's task now is to correctly identify which generator produced a particular generation. It can do it best if it distributes the task of modeling the artworks to the different generators. Now, each of the generators has a reduced task of producing images of a particular kind. For example, once the discriminator sees a fake Mona Lisa, it has to tell exactly which fake artist is responsible for making art similar to Da Vinci's style. Now, Vivek will present the results for you.
We begin with a dataset of a mixture of different object categories like forests, icebergs, and indoor scenes. When MadGAN was trained on it, we found that the three natural clusterings emerged. Each generator learned to generate images of a different type, showing its ability to do implicit disentangling of both inter-class variations and intra-class variations. Now we try to model the well-known image-to-image translation task, which is known to learn delta distribution. However, given a sketch, we could generate diverse images of bags. The generators produced bags of visually different colors and textures. Also, when given a night image, MadGAN could produce 3 plausible daylight images. Each generator consistently produced visually different, realistic daylight image in terms of weather and lighting. Now we go back to the 1D mixture of Gaussians. Even though it looks simple, here is the result of different variants of GANs. Here, the real distribution is in orange, while the learned distribution is in blue. Only MadGAN was able to capture all the modes with InfoGAN as the other contender. Please note that for all the experiments, implementing MadGAN requires changing only a few lines of code in standard GAN. Thank you, and for more details, please visit our poster at C9.
Hello, everyone. In this work, we mainly show the connection between control theory and the deep learning optimization. The PID controller used in many in the industry control field and unmanned vehicle and autonomous car. It is the core technique of the third industrial revolution. We show many connections between the feedback control system and the deep learning training. The basic unit of the control theory is the error, and the basic unit of the deep learning optimization is the gradient. And the error in control theory has the same spirit with the gradient in deep learning optimization. In control theory, the devices update based on error, and in deep learning optimization, the weight the update is based on gradient, we also show them show the connection mathematically. The PID controller has three proportional. The proportional part, the integral part, and the derivative part. We mathematically show SGD is a P controller, and SGD momentum is a PI controller. In control theory, PI controller has the overshot problem, which means if the gradient is towards one direction, the SGD momentum will accelerate the training. But if the weight want to change the direction, the SGD momentum will have an overshot problem. In control theory, we can see how PID let the three parameters influence to the training of the
the weight. So we propose the PID controller by adding a part to the SGD momentum, and this is our result on the test optimization function. Which show that the red line is our result by adding the derivative part. We can show that we can see that the derivative part will decrease the overshoot problem, and this is our result of MLP on minutes data set, and this is our result of CVPR10 on. Of CVPR10 result. We also explain the dynamic process of SGD momentum by using Laplace transformation, which is a theory from control field, and in future work we think if we see the gradient in deep learning optimization. And the error in control theory is the same thing. We may explore modern control theory for the control of the deep learning of the control field and model prediction. Yeah, model prediction. Yeah.
Good day, everyone. My name is Yerlan Idilbayev. I'm a third-year PhD student from University of California, Merced, and I'm going to make a spotlight presentation of the joint work with my advisor, Miguel Carrera Perpinan, on the topic of the neural network pruning. So let's start from motivation. With the recent success of deep learning in a lot of practical areas, like the speech and vision, it's often of interest to deploy these large networks on the computational limited devices, like mobile phones. And this requires compressing to meet the device's constraints. One way of achieving it is to prune the neural network, which is a process of removing the weights while minimally degrading its performance. Traditionally, it has been done by ranking or penalizing weights according to some criterion with possible retraining. Our approach is different and formulates pruning as a constraint optimization given original loss and pruning criteria. We want to minimize the loss subject to the pruning constraints. Our approach gives justification to traditional magnitude-based pruning in an iterative way. So let's say we want to prune a neural network having weights W, green on the slides, subject to its L0 norm being less than some user-defined kappa, which means we want to at most kappa non-zero weights. Also, we focus here on L0 norm. In our paper is applicable for many norms and criteria. So anyway, this constraint optimization problem can be equivalently rewritten as minimization over W and theta, where the theta is just an auxiliary variable copying the weights. Therefore, using penalty method like quadratic penalty or augmented Lagrangian, we can bring the equality constraints into the optimization, which yields an equation on the bottom of the slide. This equation admits an efficient alternating optimization solution having two steps. So optimizing over the weights W gives an L step that has a form of loss plus L2 penalty and independent of pruning criteria. This step will have the same form regardless of pruning and can be easily handled by any deep learning toolbox. Optimizing over the theta gives the C step, which means obtaining optimally pruned version of the weights W. It has a form of simple constraint optimization independent of the original loss and data set. Particularly, for L0 case, solution is to leave top kappa weights in the magnitude as is and 0 remaining ones. We should point out that original weights W are not pruned. They are simply marked by theta to be pruned, as theta is a copy, and therefore it is like simple magnitude pruning, but weights are not irrevocably removed. Here we show evolution of the selected neurons of the first layer of the linear 300 trained on MNIST with 5% of non-zero weights. Since pruning is not irrevocable, some weights are pruned but then revived in subsequent iterations. Even though algorithm prunes weights, we observe aggressive neuron pruning. Therefore, algorithm might be useful to do feature selection and determine the optimal number of neurons in each layer automatically. We also run LC pruning algorithm on ResNets of various sizes on CFAR10 dataset and compare to magnitude-based pruning. Thin lines is magnitude-based pruning and thick lines is LC. Since ResNets are very lean models, pruning them is harder task. As you can see from the plot, LC outperforms magnitude-based pruning and more sparsity is driven. More is the advantage of LC algorithm. Thank you very much. Please come to our poster at C13.
Hello, I'm Qu Qian from Alibaba Group. I will present large-scale distance metric learning with uncertainty. So distance metric learning is to learn a good feature embedding, where examples from same class are closer than examples from different classes. The distance metric can be learned with triplet constraint. In a triplet constraint, a dissimilar example should be pushed away from a pair of similar examples with a large margin. After obtaining the metric, the learned features can be used for classification, retrieval, and many other tasks. There are two challenges when applying distance metric learning to the vision task. First, the vision data can contain large uncertainty. For example, the uncertainty can come from the difference between individuals. For example, for the individual panda, it is unique and can be different from others. Besides, the images for the same panda can be different due to different poses and illumination. Those uncertainties may mislead the learning process and result in the suboptimal performance. The second challenge is from distance metric learning itself, which is scalability. As we mentioned above, the metric will be learned with triplet constraints. Each triplet constraint can contain 3 examples. 2 are from the same class, and 1 is from a different class. Therefore, the total number of triplet constraints is cubic in the number of original examples. Nowadays, the scale of vision task is very large. It makes distance metric learning hard to explore the triplet constraints sufficiently. And the performance is not as good as that on the small datasets. So in this work, we propose the method to alleviate the challenge. First, we will take the assumption that each observed image can be generated from a potential example. This assumption is quite natural for image data. With this assumption, we find that the potential examples have several ideal properties. First, the uncertainty is reduced in potential examples. Second, the number of potential examples can be significantly smaller than the number of original images. It is because multiple images can be generated from the same potential example. If we can learn the metric directly from potential examples, the challenges can be solved. However, the potential examples are not given. So we try to learn the metric and the potential examples simultaneously. At each iteration, the potential examples can be redefined from the original images with the current metric. Then the metric will be updated only with the potential examples. The process of learning the metric is robust and efficient. The effectiveness of the learned metric is also guaranteed, since it can not only preserve the large margin property for the potential examples, but also for the original images. Finally, the learned potential examples can be used as the reference points for a fast k-nearest neighbor classifier. So now I will show some experimental results. The left column are the potential examples recovered from the pixel features. The right columns are the corresponding original images. We can find that the recovered potential examples are more clean than the original images. The other figure summarizes the performance when increasing noise in data. The red curve indicates our method. It is much more robust to noise. That's all. Thank you.
Good afternoon, everyone. My name is Christian Rupprecht, and I will present our work on interacting with deep networks. Interaction between users and intelligent machines has gained importance as machine learning methods move into applications that involve end users. After training a neural network, inference is usually fixed and invariable. In this work, we propose a method to enable user feedback a posteriori without further updating the network's weights. This is useful because the interaction comes as an optional improvement when necessary, without compromising the original performance of the network. In this example, the network predicts a set of labels for the given image. On the top, it sees both sky and clouds. It is easy for a human to spot a mistake or suggest information regarding an image. Here, it happens to be cloudy. Our hint to the network is the sky is not visible. We want to incorporate such hints or queries from the user by inserting a spatial semantic guide into the network. The guide takes as input the user's hint, which points out the mistake formulated in natural language. The goal is to understand and translate the user's feedback into a conditioning for the network's inner activations, so that the network rethinks the inference process and improves its output. We can see that the guided network now correctly predicts clouds on the top of the image. Let's have a closer look at the guide. The process starts by embedding each word of the user's query into a pre-trained word embedding, which is encoded by an RNN. We use the last state to guide the feature activations at a chosen layer of the pre-trained CNN. We do so by predicting 3 guiding vectors alpha, beta, and gamma, which perform an update on the activations with a Hadamard product. Alpha and beta modulate the feature map spatially, for example, when providing location information or learned location priors, while gamma operates semantically by reweighting feature per channel. As a result of guiding, the following activations and the prediction change. We can also visualize the updates made by the trained guide to the feature maps. We see that the attention map corresponds to the correct region for the sky in the upper part of the image. Now, while at runtime the hints are given by a real user, during training of the guide, we simulate the human user by an automated query generator. We train only the guiding layer by directly optimizing the task loss without relying on the textual annotations for the queries. Training our query generator uses vision labels only. By comparing the initial prediction to the ground truth labels, we can identify mistakes, for example, classes that are wrongly predicted or that are missing. We can then build an error mask, split it into a grid, and extract a location based on the grid cells where the problem was identified. We then formulate varying sentences with a predefined class operation location structure and randomly sample a hint as input to the guide. The error mask is also used to weigh the loss to correctly match word semantics to visual semantics. In our results, the guide helps particularly in solving ambiguous cases, recovering partially predicted or missing objects. In the first example, the network is confused between playing field and ground. After our hint, the mistake is fixed. In the second example, the laptop is missing from the prediction, but that can also be fixed by telling the guide to look for a laptop. Finally, we show that removing noise is also possible by telling the network to get rid of the straw. We can also guide the network multiple times, even though we only trained with one hint. Here, we successively fix the clouds, playing field, and finally the ground. Finally, we visualize the t-SNE embedding of the semantic vectors gamma and verify that the guide has learned a common embedding between the user's hint and the network activations. We can see that similar types of semantic classes have similar guiding vectors, suggesting that the guide has learned to correctly map word semantics to visual categories. For more details, please come to our poster.
Hi, my name is Valentin and I will tell you about our work entitled Art of Singular Vectors and Universal Adversarial Perturbations. This is joint work with my advisor Ivan Asilides. So probably most of you heard about adversarial perturbations. So if you have some neural network classifier and we take some image, we can often construct a perturbation to this image of small norm, such that the new modified image will be incorrectly classified. And but for humans, there are no visual difference. So there are many different kinds of perturbations, but in this work, we'll be interested in universal perturbations. So they were previously proposed by Musavi in 2016, and in this case, we don't have a perturbation for each image individually. We construct a single perturbation which works for many images at once. So they also generalize across networks really well, so you can construct a perturbation using one network, and it will work for another networks too. So they look something like this. So the Previously proposed algorithm uses several thousand images to construct a perturbation with a high fooling rate. So that is, of course, a small number compared to the size of the data set, which may have millions of images. So, but perhaps we can construct reliable perturbations using a smaller number of images. So the idea is very simple. So there is a very well-known fast gradient sine method. So you take the loss function, you take its gradient, and then sine, and this will be a good, more often will be a good perturbation. So let us instead choose some hidden layer, which performs some feature extraction, and let us try to find such epsilon for a given image X, such that the features of the modified image are very distant from the original features. Then, if epsilon is small in norm, we can approximate this difference with the matrix products with the Jacobian of this hidden layer, evaluated at the point X. So, and we also have some constraint on epsilon, typically in the infinity norm. So a problem of this form is called generalized singular vector problem, and is a well-known problem in linear algebra. So in practice, if we have some network like VGG, the Jacobian is very large, so it has like hundreds, thousands by millions, and we have no hope of storing it explicitly. So instead, we have to use matrix by vector products only, and we use iterative methods to solve these problems. Namely, there is so-called Boyd's generalized power method, which is generalization of a method for finding singular values. So what to do if we want to construct universal perturbation? So we choose a small collection of images, and then we sum these distortions over this collection. And then this problem is basically the same problem as before, but with the matrix. So we stack these Jacobian matrices vertically. And to compute matrix by vector products, we use automatic differentiation and also the so-called Perron-Matters trick. So, so basically, to compute a good perturbation, we only need 30, 40 images. So there's some results. So in the table, you can see fooling rates. So they're in the range 50-60%, and also generalized across networks. And there is a nice interpretation that those perturbations, they attack low-level feature understanding. So we can see that there are edge-like noise on these images. And this is also a relatively fast algorithm, so it takes only a few minutes to find a perturbation. So to sum up, we presented a new algorithm of constructing universal adversarial perturbations, which requires very few images, and we can also modify it to use no images whatsoever with a very small drop in accuracy, so we can get like 50%. And also suggest defense approach to use the norm of Jacobians as a regularizer. So if you want to learn more, come to our poster C19.
Hi, I'm Adi from Brandeis University, and I'll be presenting our work on deflecting adversarial attacks using pixel deflection. We are all familiar with various ways the CNNs can be fooled. One such technique is to find these additive noise, and it has been shown that most of the gradient-based CNNs can easily be attacked. And it's also true that CNNs are used for many tasks, and some of them are even critical tasks. And there are various ways to try to defend against these kind of attacks. And our technique tries to find an image transformation which will try to remove some of these adversarial perturbation without impacting the clean images. So our model is based on two key insights. And the number one is that the classifier are really robust to a lot of noises, where the adversaries are not. And I will show you an example here. So here we see an image of an Indian elephant, which has been correctly classified with a very high confidence. And now, let us randomly replace the 10 pixels of this 90,000 pixel image by a random value between 0 to 255. And the classification hardly changes. If we do for 50 pixels, 100 pixels, 1,000, 5,000, 10,000, and even at 20,000 pixel, this image is still correctly classified as Indian elephant. And this shows that some of these classifiers are really robust to noise. However, here's an example of an Indian elephant which has been perturbed to be classified as guacamole with almost 100% confidence. In this case, the classifier was Inception V3. And now, if you do the similar kind of 100 pixel random replacement, already you can see the confidence of the adversarial class has gone down, and at only 1,000 pixel changes, the original class of this image has been retrieved. And the second key insight which we had was these classifiers, they really look for semantic reasons, like the parts of the object, whereas these adversarial systems are agnostic to presence of any kind of an object in the given image. So one way to look at these semantic regions is to see where the CNNs are looking for. So we'll use class activation map. So here, I'm showing you, if you look at the class activation map of these 4 images, and if you were to average this map across thousands of images, you will see a figure on the right. It tells you that most of the time objects are in the center, and that's how we take photographs. However, if you look at where the adversary is trying to change the values, they don't really care where the objects are, and they're changing every value in the pixel, whether it's a foreground or a background. Therefore, we introduce our technique, we call it pixel deflection. So we first find a random pixel in the given image, and then we draw a local neighborhood within a certain pixel boundary, and then we swap the pixels in this boundary. And by doing this within a local neighborhood, we keep the image statistics, we keep the local image statistics intact. Therefore, it doesn't impact overall classification of the image. However, it impacts the adversary a lot. And we do this more on the background and less in the foreground, so that we don't want to change a lot of the semantic content. And from the previous figure, we saw that adversaries don't really look at the objects. However, class activation maps can also be fooled, and that was one of the problem in trying to do this work. So we designed a new kind of activation maps, which we call as robust CAM, which cannot be fooled. And you can see here, our model doesn't really impact the clean images. The top row shows you the impact on the clean images. And it works across multiple classifiers, and it is one of the best defense so far. And please come to our poster C21.
Hi, I'm Makaran Tapaswi, and I present our work on teaching AI to understand social situations and human behavior. This is joint work with Paul, Louis, Sanja, and we are from the University of Toronto. Today, machines can address complex tasks such as visual question answering, and as we just saw in the earlier session, learn to perform various tasks at home. However, for AI to truly become one among us, we need to teach it to understand people and behave appropriately. Like people in the real world, characters in movies face situations such as bullying, rescuing, giving a speech, and even being lured to join the firm, something many academics know about today. We study 4 key components of human behavior. We analyze situations, both verbal and nonverbal interactions, familial and social relationships, and finally, physical and emotional attributes. Movies are split into short, coherent clips. We represent the situation within a clip using a graph. Note that characters across the clips are the same and evolve during the storyline. So let's consider this short clip from Forrest Gump. We look at the annotations associated with this clip. This is an example of bullying. We obtain a scene label and a short description for the clip. The primary component of the graphs are characters. They are associated with attributes. Jenny is worried, bullies are violent, and Forrest is scared. We label key interactions, each with topics and reasons. Bullies hit Forrest with rocks, and they insult him because he's different from them. We can also infer that their relationship is enemies. Jenny encourages Forrest to run, and he runs from them as indicated by the directed edges. Characters are grounded in the video using face tracking, and interactions using timestamps. We collect dense graphs of 51 movies, enabling long-term analysis of stories. This corresponds to over 7,500 clips. Common sense arises naturally by looking at several graphs together. For example, in a robbery, people threaten each other, while during a wedding, the couple typically agrees. Other cool features are also observed. Our dataset enables several interesting tasks. Among them, we present graph-based video retrieval, interaction ordering, and reason prediction. In graph-based retrieval, users enter graphs as queries. Our model scores individual components. We first compute similarity between the situation and scene labels. Then, we look at the characters and perform automatic ID. The overall similarity between the query graph and the video clip is computed by using all attributes, interactions, and relationships. And then we search for the best latent mapping between the graph characters and the face clusters. We show an example of video retrieval. As the query is character agnostic, it enables search across movies. The retrieved results are from different movies and have characters with similar attributes or in similar situations. Another way to evaluate social situation understanding is ordering the set of interactions between a pair of characters. Consider the interactions between the bullies and Forrest in this graph. Using an LSTM, we are able to predict a plausible order. In yet another task, we use an encoder-decoder framework to predict reasons on interactions. For example, why does C1 thank C2 in a TV show? Our model predicts sensible reasons, somehow close to the ground truth. Overall, social situations can be quite tricky. The movie graphs dataset has several other features waiting to be exploited and will be released soon. So join us in teaching AI to behave. More details at poster D1. Thank you.
Hello, I'm Alexander Matthews from the Australian National University, and I'm here to talk about our recent work on generating image captions that express a distinct linguistic style. Linguistic style can be used to communicate more clearly with the reader, connect with them, and can even sway decision-making. In this work, we look at bringing these benefits of style to image captioning. Our model, called SemStyle, generates captions that directly describe the content of the image in multiple different styles. In this example, our model is able to describe an image like a story or descriptively. The desired style can be learned from a large styled text corpus that does not describe images. The first component of SemStyle is the term generator, shown in green. The term generator both identifies image concepts and chooses which concepts should be part of the caption. We implement it as a CNN-RNN neural network and train it on images with descriptive captions such as the Microsoft COCO dataset. These training captions have been transformed into an ordered list of semantic terms, which we use as an intermediate representation of image content. The second component, shown in blue, is the language generator. It takes a list of terms as input and generates a natural language sentence. This involves choosing surface forms for each of the semantic terms and introducing new words such as function words and adjectives. The language generator is a sequence-to-sequence GRU model with attention, trained on a mixture of sentences in the desired style and Microsoft COCO captions without images. During training, the input is a list of terms extracted from either captions or styled sentences, while the target is the original caption or sentence. For training, we use two different datasets, images with descriptive captions, and a text corpus in a distinct style. In our case, the language generator was trained on a large collection of romance novels from book corpus. As judged by human annotators, the captions output by SemStyle have an average relevance score that is in line with our descriptive-only baselines. The captions are also judged as being significantly more like a story than descriptive-only captions. Here are a few examples with both story-like captions and descriptive captions generated by SemStyle. The two captions in green are considered success cases. Styled caption A is written as a sequence of actions rather than a static scene description. Styled caption B introduces a new adjective and uses poetic sentence structure. Styled caption C is my favorite failure case, consisting of an amusing realization error. Juices are not mentioned very often in the styled text corpus. If you would like to know more about our work, please come to poster D3 or read our paper. Other important aspects of our approach are the construction of the term space, the training procedure, the generation of multiple styles from a single model, and evaluation, both automatic and manual. I'm keen to talk about these topics and more. We're making our code and generated examples available online. Thank you. I hope to see you at our poster.
Hi, I'm Thorsten, and I'm going to talk about benchmarking visual localization algorithms under changing conditions. In this paper, we are interested in the visual localization problem. That is, given a query image, we'd like to compute the exact position and orientation from which it was taken with respect to some scene representation. This problem has important applications, including self-driving cars, robotics, augmented and mixed reality. There are three ways to approach the visual localization problem. Image retrieval techniques approximate the pose of the query image using the pose of the most similar database image. Structure-based methods establish correspondences between pixels in the query image and 3D points in the scene and use these 2D, 3D matches for pose estimation. Post-regression techniques directly learn the mapping from image appearance to 6-stop camera poses. What's common to all of those approaches is that they take a set of database images and compute a scene representation. And they work well if the query images are taken under similar conditions as the database images. But it's unlikely that we're able to take database images under all conditions of a scene, meaning that it's important that localization algorithms are robust to changing conditions. As shown on this slide, this is a hard problem as there can be severe changes in image appearance and scene geometry between, for example, seasonal changes. And we are thus interested in measuring the robustness of different localization algorithms to such changes. In this paper, we propose 3 new data sets based on existing imagery to do this evaluation. In more detail, we select images taken under a single condition and then for each dataset compute a reference 3D model using structure for motion. We then selected query images taken under different conditions and estimated accurate reference poses for them that can be used for evaluation. We then used the whole benchmark to evaluate state-of-the-art localization algorithms on them. We're going to make that benchmark publicly available later this year. The first benchmark dataset is the Aachen day-night dataset, where we used daytime images to build a 3D model and then query with high-quality nighttime images taken by a smartphone. This dataset represents a handheld augmented reality scenario. The second dataset is the robot car seasons dataset, which simulates a self-driving car scenario where we query with images taken under a different seasonal weather and illumination conditions. And that's mostly in an urban scene. The last dataset is the CMU seasons dataset, which again looks at self-driving cars, but in a more vegetated environment where seasonal changes have a much stronger impact on scene appearance than in urban environments. Besides creating those 3 benchmarks, we also evaluated state-of-the-art localization algorithms on them, and that includes image retrieval techniques, structure-based methods, and trajectory-based approaches that query with multiple images at the same time. We also evaluated the impact of different local features on localization performance and tried out post-regression techniques, but found that those didn't really work on our datasets. To conclude the talk, so what we have created is 3 novel benchmark datasets for long-term visual localization, each providing a reference 3D model, query images taken under different conditions, and reference pose for those images. Our results show that there's significant room for improvement on those datasets. We're going to release that benchmark later this year. If you want to know more about it, please come to our poster D5. Thank you very much.
Good afternoon, everyone. I'm Liu Feng from South East University. Today, I'd like to introduce our work, IVQA, Inverse Visual Question Answering. This work is jointly work with Professor Tao Xiang from Queen Mary University of London and Professor Timothy Hospitalis from University of Edinburgh. The language bias in VQA motivates our work. Recent studies find that VQA models achieve high scores without really understanding the image content. The following is an example. Language bias means that applying a question on different images often results in the same answer, even though the true answer varies by image. Here's another example. The image shows a tray, not a basket, but the wiki model's confidence in predicting bread is larger for basket than tree. This is because the correlation between the question and answer is overexploited. Due to this limitation, we want a problem that is less biased, more demanding for understanding of the image content, and could complement existing benchmarks. RVQ is such a problem. RVQ aims to generate visual questions based on image and a keyword, where the keyword is the answer to the question in the context of that image. Here's some examples. Given the answer yes, the RVQ model generates questions to fit both the image and the answer. As the answer contains limited information, there is less language bias to be exploited, and the model must turn to the image for cues to generate valid questions. It is a challenging problem. Firstly, as the textual cue is limited and the visual information is too abstract, it's hard to decode such information directly. Secondly, since the detail about the image need to be discovered, the model should know which part of the image the answer is referring to. So we designed an RVQ model with two main modules for gradual question generation: the initial glimpse and dynamic attention. The initial glimpse won't start the decoding process, generating the initial words in the question. The dynamic attention attends to the right feature for predicting each word. Unlike VQA, RVQA is a one-to-many problem. This means that it's not accurate to simply compute cider or blue scores between generated questions and the references. For example, given this image answer pair, all generated candidates are correct, but none of them match the annotated ground truth. Therefore, we perform human study. Human studies are effective, but not efficient. So we propose a ranking-based automatic measure where ground truth questions are placed among distractors in a pool. The RVQ model ranks the question based on their probability. The ranking of the ground truth question correlates well with the human study scores. In follow-up work, we show that RVQA can be used to diagnose these VQA models. Given an image answer pair, we use RVQA to generate candidates and apply them to the VQA models. This reveals QA pair that a given VQA model believed to be true outside the dataset. Interestingly, we found the popular VQA models have many more false beliefs than expected. If you are interested in our work, please visit our poster, D7. Thank you.
Hello, my name is Alberto Marola, and today I'll be presenting our work titled Unsupervised Person Image Synthesis in Arbitrary Poses. So in this work, we've tackled the following problem. Given an input image of a person in an arbitrary pose and a desired 2D pose, our model is capable of generating a new photorealistic image of that person under the desired pose. So previous works approach this problem in a supervised manner. Instead, we here present a generative-based model trained in a completely unsupervised way. What I mean with unsupervised is that it would be easier if we had a large dataset of triplets containing both the input image and the desired 2D pose, along also with the desired output. Instead, in this work, we only have a set of images of people, and its corresponding 2D pose. That's all we have. And with only that, we will have to learn the intrinsic geometric and texture properties of all three deformable elements involved, so cloth, body, and hair. Here we show a diagram of our model, and as you can see, there are a lot of components involved in it, so we will dissect it and go step by step in order to better understand it. So at the beginning, we only have a generator, which given an input image and a desired pose can only generate noise. So first we add a discriminator to generate photorealistic images. Also, in order to constrain the generator with a given pose, we use a pose regressor to penalize the difference between the desired 2D pose and the pose of the generated image. So notice now in the image in the middle then we can generate photorealistic images of people on the desired pose, but still we cannot maintain texture. And in fact, this is the most challenging part. So first we add a cycle loss. But as we prove in the experimentation, this is not enough. It's still extreme for this extremely post problem. So we propose an extra identity loss that draws inspiration on style transfer problems, as it's also evaluated on style and content, but we've given to the style a twist. So we are not interested in evaluating the image as a whole, because that would mess with the image by mixing the texture of the different parts of the cloth. Instead, we only compare texture around areas that we know to be spatially correlated. So for example, we would like the texture around the shoulder to be similar between the input and the generated image. So what we do is we compare the texture around the visible joints, and we left the rest unevaluated. Here we show some results. So given an input image and a desire to depose, our model generates a new photorealistic image, and here we can compare with ground truth. Remember that we didn't train with ground truth. This is here just to show it. But of course, our model is still not perfect. Tackling such an unconstrained problem in a fully unsupervised manner causes a number of errors, like incorrect texture mapping, missing limbs, and keeping relevant information in cycles that we are now tackling in order to improve it. So to conclude, we have presented a generative-based model capable of synthesizing images of people in arbitrary poses in a complete unsupervised manner. And we also have proposed a novel layer to preserve texture across images. Thank you. I'll be more than happy to answer your questions on the poster.
All right, this concludes the session. Let's thank all the speakers again.